let's now go to step 3. So step 3 is going to be effective only for this last term in this derivative. And the identity that one uses is this one. You see, when you convert this j derivative on the right hand side to this expression, after taking j going to 0, this is going to become a g2, g connected, and then there is an additional derivative with respect to phi cl. So with u integral, we can call it u4, and then we can write this last term. So let me begin by writing the last term. So I have written this at the wrong place. What we are calculating is g4 connected x1 to x4. That was the left hand side. On the right hand side, the last term, let me write down that one first by applying that identity, and that will be minus I by h bar times integral du1, du2, du3, and du4. That u4 is coming because of using this identity, this extra u integral, and there is a g2 between x4 and u4, and there is an extra derivative with respect to phi cl at u4. So we will have the same terms except that now I will have a del phi cl at u4 and there is a factor of g2c x4 u4. This is what the last term would look like. And then the other three terms, let me write them down, just copy them without processing them any further. So now our strategy is going to be look at this last three terms diagrammatically. So if you do that, then what is the diagram? Because now, okay, so now whatever these three lines are, these three expressions are, they are all, you know, we all have, they are well identified. They have appeared in our previous calculations, and therefore we can go back to our diagrammatic notation for this, for these terms. So let us do this. So there is a each one. Let us look at the first one. It has a gamma 3, which is minus I by h bar gamma 3, and we have already established that that is the 3.1 particle irreducible diagram. So that is 1 pi with 3 points which are u1, u2, and u3, and From U3 and U2, there are connected Green's function, which are going to. So let us see how they look. So this is X3 and this is X2, right? There are two connected Green's function from X2, X3 to the 1 pi vertex, 3.1 pi vertex, and then there's a connected 3-point function X1, X4, and U1. So this is U1, and then from U1 I should be drawing a connected 3-point vertex, and they are going to X1 and X4. But this is same as 1 pi X2 C X3. Now a connected 3-point function, we already know that a connected 3-point function is related to, this is what we found earlier, right? I mean, a connected 3-point function is related to the 3.1 pi vertex in this way, which also has a diagrammatic representation, and the diagrammatic representation here is nothing but, we can do it here. What we saw earlier. So it is 1 pi U1, U2, U3. That is what a connected 3-point function is. This is on the right hand side. On the left hand side, it is right. So we are going to now, whatever a diagram that we have there is basically this structure. We replace this by this. X1 and X4. So that is the diagram for the first line. Similarly, you can do the same exercise for the second and third line as well. You see those are related to this first one by some interchange of x's. Let's see. So first line and second line are related by interchange of x1 and x2, because x4 appears with x1 here, x4 appears with x2. u1, u2, u3 are dummy variables, and they can always be interchanged. And the third line is interchange between x1 and x3. Now, if you interchange between x1 and x2, then you get that one channel, and x1 and x3 if you go to the result for gamma 4, where we explicitly drew all the diagrams. Let me try to figure out here. So this look at this topological diagrams. These three in the calculations of G4. This tree level this tree level diagrams appeared, and then a 4 vertex. So did we have any position space? No. Okay, fine. Okay, I can explain here. So if you now if you rename, if you give names x1, x2, x3, x4, then you can show that these other two diagrams are basically interchange with x1, x3, and x1, x4. So if this is x1, this is x2, this is x3, and this is x4, then other two diagrams, so this diagram, for example, is same as changing x1 and x3. So this is x1 and x3. This is changing x1 and x3 because then these two are interchanged. So that is this diagram. And if you interchange, so x1, x2, x3, and x4, if you interchange between x1 and x4, then you get this other this channel. So if it is x1 and so this is x1, x2, x3, and x4. Now interchange x1 and x4, then you see here in this diagram x1 and x2 are going to one single vertex, but when you interchange x1 and x4, then this will become x1, and then x1 and x2 are going to two different vertices. That is basically the difference between these two channels. And look at these two lines, they are going to the same vertex. In this diagram, they are going to two different vertices. That is why these are two different channels, two different topological channels. And so that will happen. So basically what I'm saying is that you interchange the label of one with just the opposite and one from here. Do not change with this one, then it is the same topological channel. You interchange with the opposite two, so then you will generate these two diagrams. That is precisely what is happening here as well. This diagram, so this is the first line, then the second line is x1 interchange with, as I mentioned, x2 plus x1 interchanged with x3. Now let's look at the configuration here. So this is x1, x2, x3, x4. So exactly, x1 is getting interchanged with the opposite 2 points, and therefore will produce those topologically inequivalent channels, right? So then since we already know that result, we know that diagrammatically, so let me see here. This is equal to this diagram, which is same as this diagram, plus these two diagrams, and then plus the first term. And that first term, we know from previous result that this G4 must be these three diagrams plus this diagram, the 4.1 pi. And therefore, this diagram must be this one, the first term, and therefore the 4.1 pi must be this one. But we know that the 4.1 pi, which is given by, say, gamma 4, and then this analysis implies that gamma 4 u1, u2, u3, u4 is same as delta 4 gamma phi cl divided by del phi cl u1 del phi cl u2 del phi cl u3 del phi cl u4. At 0. That is the result we wanted to prove. That is the original result that we set out to prove, which is this one for n equal to 4.